Okay, hopefully we are back. So I am just going to go down the row here of people who are showing up on my computer and ask questions. But I need to record whether or not you're participating.
Hey, Professor.
Yes.
Before we get started, just because I would hate to be caught at the bottom, and I know other people would too. Is for number 7, just 'cause it's a little bit more complex. It's talking about the blocks being held up. So is that just a ratio of acceleration to gravity, which is if it I'm sorry, this isn't MKS, but it's
No, the block is held up because there's a frictional force between the block and the cart.
Okay, so it's not a ratio of acceleration, gravity, or anything like
that?
Okay.
No. Okay, there we go. All right, let's do the Atwood machine. So, Andreas, we'll call this block A.
Okay.
Would you please draw for us a free body diagram for block A? Can you annotate?
I'm going to, yeah, I believe I can.
Okay, now if you want me to draw it for you, you tell me what to draw. That's okay too.
So for block A, oh, that's supposed to be an arrow.
Okay, good.
So that's mass times gravity.
Okay.
And we have an upward force. And I believe this upward force would be from the mass and gravity of what would be block B?
No.
Acting on it?
No.
Or is that simply
they're connected by a string, so there's tension in the string pulling up on block A.
Okay.
So that force is the tension force. It's not MBG.
Okay. So then that force would just be the tension from the rope or the string.
That's correct.
Okay.
That's correct. Okay, very good. All right. Luis Cornejo, can you do a free body diagram for block B, which is this one right here?
Yes. How do I edit?
You annotate by going to view options and hitting annotate. You can just tell me what to write if you prefer.
I got it.
Okay, good. Okay, you've got the right idea. But let's develop a convention for this. Put a little dot there. Don't actually draw the block. And have the arrows come out of your little dot. So this becomes mg, and this becomes the tension force, or F sub t if you prefer. But that's essentially what you wrote, right?
Yeah.
Okay, very good. Okay, Benjamin. For case A over here, well, actually, I'm sorry, for both, there is an equation of constraint that links the motion of block A to the motion of block B. So can you tell me what the equation of constraint is? Or you can just describe it in words.
I would say, I would say essentially that block B goes down and block A goes up.
They're connected by a string that doesn't stretch. So what can you say about their accelerations?
They're equal in opposite directions.
Perfect. That's exactly correct. So the equation of constraint, which you actually need as an equation to solve this problem, is that the acceleration of block A is minus the acceleration of block B. And when you write down the equations of motion for this, you will need that equation in order to solve, because you'll need another equation besides F equals ma, which is in fact the equation of constraint. Okay, very good.
Professor, why is the one negative?
Because if
Oh, it's
A
just
goes
direction.
up, B goes down. And if
Okay,
A goes down, B goes up.
okay, you don't just treat acceleration as movement.
Well, we have to, it's a vector, so we have to give it a sign in a one-dimensional problem. It's either positive or negative down.
Okay.
Okay, good. Okay, we have a block sitting on an inclined plane. That's part A. Let's do part A. Matthew, Portugal. This is the mass M of the block. It's sitting here, it's not moving. So draw a free body diagram for it.
Sorry, how do you get it again?
Go to view options. Click on annotate.
Can't find view options. Can I just tell you what's the right?
Yes, that's absolutely fine.
So in the downward direction, I have the mass times gravity. And in the other direction, I have the friction force in the northwest direction.
Okay, so friction force is along the plane, so it's like this. I'll call it left.
And then that's what I had for it, but I can maybe
There's one more. There's one more.
Force of the block.
The normal force is the wedge on the block.
So
The block is pushing, or the wedge is pushing that way.
okay. So for that one, let's see. I would say it would I also use the mass times gravity for the block?
Well, you've got that. You've got the mass times gravity of the block. You've got that pointing straight down. So the normal force just points this way.
Oh, yeah. Okay.
Yeah, that's those three.
All right, okay.
Very good. All right, so Jonathan.
Yep.
What's the constraint on the motion of this block?
It's that both of the blocks are moving dependently, like together.
Well, they're not moving at all,
Oh, I'm sorry.
right? It's part A.
Oh, okay. Yeah, it's that they're not moving and gravity is acting on them together.
Well, yes. Well, the gravity doesn't make any difference. Gravity will certainly act on both of them. We only care about the block. So the equation of constraint is that the acceleration of the block is equal to 0. And that means both the x and the y components are 0. So you have an equation for the x component and an equation for the y component, and each of them have to be equal to 0. Does that make sense?
Yeah. So is basically the constraint just like the key to solve the problem, basically? Like you're finding that one little bit?
The constraint is a key to solving the problem almost always. And usually it'll be something very simple like this. Occasionally it'll be something more complicated like the Atwood machine. And sometimes it'll be something very complicated. And a lot of thought is sometimes put into the equations of constraint. Okay, so this is part A. Now for part B, Christopher, the block is sliding down the plane, but the wedge is motionless. So why don't we do the free body diagram for the mass?
Okay, so the mass would be going down to the right.
It's sliding down.
Can you draw it?
Yes. So here's the mass. What are the forces acting on it?
It would be gravity.
Okay, what else?
And then you have a friction force since it's moving.
Okay, and what direction is the friction force?
It'll be going opposite the way the block is moving down. So same as before, up to the left.
There we go, correct. And there's another force.
The normal force is still acting on it, right?
Of course.
So that would be, again, up to the right.
Anything else?
I feel like yes, but I'm not sure.
No, there's no more.
Okay.
Now, here's the point. The point is the student sometimes thinks that the motion affects what the free body diagram is. That's not correct.
Okay.
The free body diagram tells you what all the forces are. And those forces determine the motion. So whether the block is moving or not, the free body diagrams are exactly the same.
Okay.
Now, what about the equation of constraint? That's much more complicated. So, Adam, you wanna tell me in words what you think the constraint is on the motion of that block?
Would it be the tangent of the angle at the bottom right, like the height over the length?
Tell me in English words. Don't give me the mathematics. Just tell me what's happening in plain English.
It's how steep it's sliding down.
I think what I'm asking you is something you're making it more complicated. You know this. The constraint is that it stays on the inclined plane, right?
Yeah.
Yeah, so it stays on the inclined plane. So you can put a constraint on the motion of the X and Y components of Z, or you can do something more simple. And we're going to do this with almost all our inclined plane problems. Going to change our axes so that this is the y-axis and this is the x-axis. And you can do that. You can figure out what all the angles are, put the angles on the diagram, and you're good. But what's the point of doing this? The point of doing this is that your constraint is that a sub y is equal to 0. It doesn't move off the plane in that direction. So a sub x is one of the unknowns. But a sub y is 0 because of the way I define the coordinate system. And we're going to play that trick quite often. Okay. For number 4, we have a mass A and we have a mass B. Aman, would you like to do the free body diagram for mass A, please? For A, please. Now just write it as a dot. Don't actually. You can. That's fine. You can do it this way. That's fine. Keep going. Keep going. Keep going. You're good. Just keep going. Good. Good. Okay, good. That would be. I didn't say that the surface was frictionless, but if it were frictionless, you would be correct. What if there were friction between block A and the table? Include that force now, assuming it's there. There we go. Yes, there we go, exactly right. So if there's friction, it opposes the motion. The motion is to the right. So there you go. Very good. Just call it little f for friction. Good enough. Just you use any names you like, but that's my convention. Okay, very good. Okay, Daniel. Why don't you do the free body diagram for B before we talk about the equations of constraints? So do the free body diagram for B. That was fine. We don't care about points for neatness, Daniel. Okay, so B stands for the mass of mass B, right? Okay, that's good. That's good. Is there anything else? Is there anything else, Daniel?
He's typing. He said air resistance considered friction, and then I think that's it.
Yeah, we're not going to include air resistance, and so you're right. That's it. Okay, very good.
Professor,
Yes.
for that one, like you wouldn't include like the tension on the rope from the friction? Like the friction
Oh,
from
you're
block
talking
A?
about friction on the pulley? Right here?
Oh, I guess you're right, because there'd just be tension up, right?
Yeah,
Yeah.
we're gonna consider the pulley to not have any sliding friction and to not have any mass.
But what
So-
about like, the friction from A?
Oh, well, that acts only on A, it doesn't act on B.
Okay.
It has an effect on the dynamics, but it acts on body A. So it's included in over here in the free body diagram for body A. It is not included on the free body diagram for B. The fact that this friction is here affects what the tension is, but you have to solve the equations to find out what that effect is. Okay, now there are equations of constraint here. One equation of constraint concerns only A, and the other equation of constraint concerns both A and B. Shifa, you have any ideas?
It's moving in a downwards motion because of B.
Well, A is moving to the right if B is moving down. So what can I say about their accelerations?
A is dependent on B.
Exactly, but specifically, the acceleration of A is minus the acceleration of B. Because A moves to the right, which is positive, we call that positive, and B moves down, we call that negative. So the accelerations have opposite signs, but they have the same magnitude because they're connected by the rope. Okay, Shifa, there's one more equation of constraint. It has only to do with A, doesn't involve B. Just think physically what's happening. How is A moving?
Because of B.
No, of A. How is A moving? Okay, I'm trying to get you to say it's moving horizontally.
Yeah, it's moving horizontal.
So is it accelerating in the Y direction?
Yeah.
No, that we're calling that X. Horizontal is X, Y is vertical. So is it accelerating in the vertical direction?
No, horizontal.
Only horizontal. So one equation of constraint is that the acceleration of A in the Y direction is equal to 0. This is for A only, because obviously B is accelerating in the Y direction. So that means that N minus mg, which is ma sub y, is 0. So that equation of constraint allows us to solve for the normal force. This equation of constraint allows us to solve for the friction and the tension. And we'll see again later, shortly, we'll actually solve problems and you'll see how it works. But the first step is to write down the free body diagrams and to understand what the constraints are. Okay, Tuan. Let's look at number 5. And I made a mistake here the block is mass A, but the wedge, we also have to do a free body diagram for because the wedge moving is part of the problem. Now, the block does not move with respect to the wedge, but the whole thing moves to the right. So Tuan, why don't you do a free body diagram for me for block A? That's okay. Don't worry about it being at a funny angle. It's hard to draw with the mouse. Okay, that's better. Okay, good. No, that force is applied to block B, not to block A. So the applied force FA does not act directly on A, but other forces do. Okay, you had this correct. I'll rewrite it for you. I know it's hard to write. M sub A times G. Okay, very good. So what force is that one that you just drew? Good. Okay. And now there's one more force. Good. Okay. That's great. Okay, very good. Now, Joshua, I want you to do a free body diagram for the wedge B. And be careful because this one is a little bit tricky. Are you there, Joshua? Okay, Josh, go ahead and do the free body diagram for the wedge B. Okay, we'll come back to you, Josh. Aurelio, can you do a free body diagram for the wedge B?
Yes.
Okay,
Do you mind writing it while I tell you what to do?
not at all. So here's B.
Great. So there would be mg, the weight down.
Okay,
Then there would be the force acting on B towards the right.
so that's the applied force, FA.
Yes.
Okay,
And then there would be a friction force to the left of the free body diagram.
Okay, you're saying there's friction right here with the floor.
Yes.
That's fine. That could be. So let's write that as friction from the floor.
And then there's the weight of A on top of B.
Aha, but that is the reaction to the normal force of B on A. So there is a reaction to this force, and it is N in this direction. Very good. There's one more, and it's the one that everyone forgets.
Friction.
It's there's a frictional force between A and B, right?
Okay.
So on A, it acts this way. Which way does it act for B?
The other way, so down.
Okay, so it acts this way. So there's another force here that is little f. Actually, there's one more force. We left it out.
Man. So it would be the weight acting on A. Weight of B acting on A.
No, the floor pushes up. The floor pushes up. So the force of the floor. See how the floor has to push up on B this way?
Yeah.
Okay, so this is all of them. Here is the point. This one here has a reaction down here. Students sometimes forget that. The frictional force here has a reaction in the other direction, which is this one. And students always forget that one. But that has to be included in the equations. Okay, that was a hard one.
Professor,
Yes.
Is there a normal force from the applied force to the left?
On B? No, there's
Yeah.
just the applied force on B. Now, the fact that you have that applied force affects all the other forces. But FA, this one right here, only acts on block B.
Okay.
It's tempting to want to say, well, if it's acting on B, then it must be acting on A. But that's not true, because it isn't the applied force FA that's making A here accelerate. What's making A here accelerate is the normal component of N. So N pushes on this, it's that makes A accelerate.
Can you clarify that point a little bit more?
Sure. Let's, here, I'm gonna erase some of this stuff here. Okay. FA pushes here, and that accelerates this whole thing. However, it isn't FA that accelerates A. The thing that accelerates A is this normal force right here. That has a component horizontally, and it's the horizontal component of N that causes this block A to accelerate. F is applied only to block B.
I'm just kind of trying to think about like the jerk and like Newton's first law is like kind of like what I'm thinking, like why doesn't that affect it? Like why doesn't it want to stay stationary while it does move?
It stays stationary because you're pushing it fast enough that you're making N great enough that the frictional force is great enough to keep it from falling.
Oh, okay, got it.
Yeah, the jerk has nothing to do with it. Jerk is nothing but the derivative of the acceleration. But all the accelerations in this problem are going to be constant. Oh, and equation of constraint. So who haven't I called on? Sophia. Okay, Sophia's not here. Desiree? Okay, Desiree's not here. Luis Soriano?
Can I give it a shot?
Hold on a sec. Oh, and Joshua, we're coming back to you. Joshua, did you fix your problems with your mic? Okay. All right, Joshua. I'll ask you a simple question. You can answer it in the chat. What is the equation of constraint? There's something that constrains the motion of both A and B. So how would you express that constraint? Okay, did Joshua go away? Is he restarting his computer? All right. Okay. Michelle Bailey. And Alvaro Mata.
Yeah.
Oh, you're here. Okay, good. All right. Why don't you answer Joshua's question? We'll give him another one. What's the equation of constraint for this situation in number 5?
So would it so A and B are moving together as one whole thing?
Yes, and A is not moving with respect to B. So they're rigid like this and moving to the right. Very good. So can I express that as an equation?
But the be that the accelerations are equal?
There you go. It's exactly correct. The acceleration of A in vector sense must be equal to the acceleration of B. And neither of them are accelerating in the y direction. So A sub y is equal to 0 for both of them. But the x component of acceleration is the same for both. Okay, that was very good. Okay, Truck, Win? Are you here, Truck? All right. Well, the only person who hasn't had a chance to do something here is Joshua. Let's wait till he gets back online. Are you back, Josh? Doesn't look like it. Okay. The monkey is pretty easy. Let's do a free body diagram for the monkey. I have the mass of the monkey and the tension in the rope. And for the block, it's in the air. So I have the tension pulling up, and I have the mass of the block times G pulling down. Now, I don't know the equation of constraint because I don't have any information. Is the block still? Is the monkey accelerating? You have to be given that as part of the problem in order to figure out the equation of constraint. But notice that I have two equations here, and I'm going to have three unknowns. My unknowns are going to be T, the acceleration of the monkey, and the acceleration of the block. So I'm going to have to be given more information in order to solve this problem. And number 7. Okay, for this first case, I have the cart, I'll call that B, and I'll call this mass A. For the cart, I have the mass of the cart times G. I have the normal force of the floor. I have the applied force FA. Oh, and look, I'm going to have a normal force between B and A. So the normal force of A on B works this way. So I'm going to call that N. And now I have a frictional force holding A up. So for A, the frictional force is like this. For B, it's the reaction. So it's down. So little f is down. Now, what about A? Well, I have MAG. I have the frictional force acting up, and I have the normal force this way. So this end right here is the same as this end right here, but they're in opposite directions. Just like this F is the same as this F, but they're in opposite directions. Okay, that's good. Now, this problem here, I'm going to let you work on your own. I'm going to put this on your test. So work on it, and you may ask questions about it, but I will put it on your test. Okay, does anybody have any questions on free body diagrams?
For that last one, when you made the cart B, would there be a friction force opposing the force of A?
Oh, you're saying, is there a friction force here
Yeah.
on this surface?
Would we
I'm going
incorporate
to,
that?
yeah, actually, you need to know this. This has to be told to you. We're going to study something when we study rotational motion called the smooth rolling condition. I'm going to assume that the smooth rolling condition is satisfied, and therefore these roll smoothly without friction. So there's no friction here. There could be, you could add it in if you wanted to, but we're not going to.
Okay, thank you.
Okay, very good. All right.
Oh, I have a question.
Joshua, oh, go ahead.
So I'm still trying to understand equations of constraint and what that means exactly. Like, could you explain that a bit more?
Sure, equations of constraint are just an equation that tells you how the motion is constrained. For example, the equation of constraint, actually, Joshua, see if your mic works. Talk to me. Okay, obviously your mic isn't working. All right. So the question was about equations of constraint. So what's the equation of constraint for this thing? Well, the equation is that since these two things are rigidly held together, the acceleration of B has to equal the acceleration of A. So you would have, if I asked you, is that true? You would say, well, yeah, of course it's true. They're touching each other and they're not moving with respect to one another. So they've got to have the same acceleration. But putting that in equation form gives you another equation with which to solve the problem. And you'll need another equation to solve this problem here. But we'll do examples and you'll see exactly how it works. All right. Okay, we've got about half an hour. So you know what? Let's actually start solving some problems so that we can get an idea of how to put all this together. And in fact, let's solve this one right here. So my free body diagram for the cart is the normal force of the floor pushes up. MBG is down. My applied force is this way. The normal force, which is A pushing back on B, is this way. And the friction force between A and B acts upward on A, therefore downward on B. Now let's do the free body diagram for A. I have MAG. I have the normal force between B and A accelerating. So that's the reaction to this action right here. And I have the frictional force F pushing up. Oh, and I just realized something. We can't actually solve this without a model for friction, but let's set up the equations anyway. So there's going to be 4 equations because I have 2 directions for the 2 bodies. So for the vertical direction, I have N of the floor minus MBG minus little f is equal to what? That's equal to 0 because B isn't moving up and down. It's only moving in the horizontal plane. Now, in the horizontal plane, I have FA, or direction I mean, FA minus N equals MA times the acceleration of A. So it's going to be accelerating to the right. So I can't put 0 there. I've got to put A. A is an unknown. Now let's write down my 2 equations for this free body diagram. F minus MAG, well, is A moving up and down? So that's 0. And what about the horizontal direction? I get N equals M sub A. Oh, this is A sub B, not A sub A. Darn it. Okay, you guys got to say something. This is B, not A. So this becomes M sub B, A sub B. I'm sorry. Okay, so N equals M sub A sub A. Now, let's look at the number of unknowns we have and the number of equations. So the normal force of the floor is an unknown. The frictional force is an unknown. FA is considered known, so the acceleration of B is unknown. So I have 3. Now I have, oh, I forgot, this N is an unknown. And I have A sub A. So I have 4 equations and 1, 2, 3, 4, 5 unknowns. I need another equation. My second equation is that A sub A equals A sub B. And now I can just write this as A and this as A. And now I have 4 equations in 4 unknowns. And I actually can solve for the frictional force F. Okay. Yeah, I think that's good enough for now. All right, does anybody have any questions on how I set up these equations? All you do is do the free body diagram, and in each direction, if it's a 2-dimensional problem or 3, in each direction, just write F net is equal to MA. Sometimes A will be an unknown. Sometimes A will be 0 if it's not accelerating in that direction. But you'll always be writing basically this equation. Okay, let's do another problem. Let's consider a mass here on the end of a desk or a table. And I've got a pulley here, and this pulley is an ideal pulley. What is the point of an ideal pulley? The ideal pulley doesn't contribute to the dynamics. All it does is change the direction of the motion. In this case, it changed the direction of the motion of the string from horizontal to vertical. Let's call this M1, and let's call this M2. Now a free body diagram for M1, and we're going to say that there's no friction on this surface. So this surface is frictionless. So we have M1G. Here we have the normal force of the table. And here we have the tension of the string. For B, we have, or for mass 2, I meant to say, we have M2G and the tension T. Oh, come on, give up. Thank you. All right, so let's write down the equations of motion. We have N minus M1G is equal to 0. Well, that just tells me what the normal force is, but that equation doesn't do any good for me right now. I also have the tension T is equal to M1A sub 1. And for mass B, I have the tension T is, I'm sorry, minus M2G equals M2A2. Now I have, for these two equations here, because this third one doesn't matter, I have 1, 2, 3 unknowns, T, A1, and A2. I need another equation. And my other equation is that A1 equals minus A2. So I have T equals M1A1, and I have T minus M2G equals minus M2A1. Well, now I can solve for the acceleration. T is M1A1, so I have M1A1 minus M2G equals minus M2A1. So A1 is equal to M2G divided by M1 plus M2. So that's the acceleration. Let's look at some limiting cases of the acceleration. What is the limit as M1 goes to 0 of A? We'll just write it as A instead of A1. What is that? Well, as M1 goes to 0, that's 0. The M2s cancel. So the acceleration is just G, which makes sense. M2's in free fall because M1's not holding it back. What's the limit as M1 goes to infinity of A? We'll let M1 become infinitely large, then this term dominates. 1 over that term, A is equal to 0. So if M1 is infinitely heavy, then M2 is not going to move, and neither is M1. What about the limit as M2 becomes infinitely large? Well, if M2 becomes infinitely large, M1 can be ignored, M2 cancels. Oh, look, we get G. So if M2 is very large compared to M1, it's just going to fall as if it's in free fall. Okay, that was an instructive problem. So when you solve these problems, after you solve them, you want to do a couple of things. The first thing is to check units, and I didn't do that. But mg over m gives me just g, and a and g are the same units. That's correct. Then I want to look at limiting cases. I never bothered to solve for t, but t is equal to m1 m2g over m1 plus m2. What about the units here? Well, the units m here cancel with the units m here, and I get mg as my units of tension. So tension's a force, and mg is a force. So the units are correct. Okay. There's other things you can do with this, but let's leave it for the moment.
Professor?
Yes.
My laptop just died, so I missed this last section. Was this just like another example, or was it like
This is just an example.
problem?
This is an example. I don't
Okay.
think it's a homework problem. It's just an example.
Got
Okay.
it. I took a screenshot and I'll just copy it down later.
Okay. Let's do a problem with a wedge. So here's a wedge. My wedge angle is theta, and I have a block sitting here. Let's assume that there's no friction between the block and the inclined plane. Let's pull on a rope here with the tension T. And we'll just call this M. Now, the easiest way to solve this problem, and you will do this all the time, is to redefine your coordinate system so that the x-axis lies along the plane and the y-axis is perpendicular to the plane. So this is the x-axis and this is the y-axis. Now, let's do our free body diagram. Here's the mass M. Now I'm going to superimpose on it this coordinate system. So this is the x-axis, and this is the y-axis. Now, what are the forces that are acting? Well, I have mg acting straight down. So that is mg. I have the tension acting in the positive x direction. So that's the tension T. And I have the normal force acting in the y direction. Now without friction, those are the only forces. So let's consider this without friction. This angle right here is the angle theta. So you see from the description that this must be 90 minus theta, and this must be theta. So my equation in the x direction is T minus mg sine theta. So everyone see how the component in this direction is m sine theta equals m a in the x direction. Now let's assume that it's confined to stay on the plane. Then in the y direction, we have n minus mg cosine theta must equal 0. Now that's a basic setup. And you can add other constraints. For example, I could say, if I want to hold that block motionless, what is the necessary tension T? Well, if it's motionless, that's 0. Now I solve T in N. I could say, if I'm given T, what is the value of the acceleration? It could be either positive or negative. Depending on the value of T, I could go up or I could go down the plane. Okay, because this is something you need to get used to. Just like with the projectile motion problems, shooting a ball down a cliff, shooting a ball off a cliff, changing the axes to a more convenient location is frequently a good strategy. And in this case, it makes this very easy to do this problem. All right, that's pretty good for today. Does anybody have any questions? All right. Okay, then if no one has anything they need to say, then I'll just wish everyone a very good weekend. And I'll see you again on Monday.
Have a good one, Professor.